Hello everyone, my name is Patrick. In fact, so in this video, I'm going to present our work fairness under demographic scarce regime. This is a joint work with Samira and Ulrich. So here's the outline of the presentation. I'll start by giving like an introduction with some background, and then we provide the methodology of our work, and then we present the experimental results and conclude with future work. So for the context, machine learning models are becoming increasingly used in high-stake scenario where decisions that are provided can have profound impact on people's life. And those domains span from finance, criminal justice, hiring, or education. Because of the importance of these decisions, ethical implication has been raised, and for that, there are ethical principles that guide the design and deployment of machine learning model that include fairness, privacy, accountability, and transparency. And in our interest, it has been shown that uh, machine learning model can learn and sometimes even perpetuate bias in the data. So for this context, we are interested in this work in a classification problem where we are given a set of input features that could be applicant credit history, or also giving a set of each sample it has like a target variable that can be like allow or deny a loan, and also we have some protected attributes which are gender, race, or any attribute that the model should not rely on to make decisions. So the task that we are interested in is to design a model that can accurately predict the target variable while being fair with respect to different demographic groups that we have in our data sets. And for this, the first question is what do we mean by being fair for a machine learning model? So there are a lot of definitions that have been proposed, and in this work, we're interested in three main definitions, which are demographic parity, equal household, and equal opportunity. So demographic parity basically enforces the output of the model, which is y hat here, to be independent of the sensitive attribute. On the other hand, equal household will basically enforce the true positive rate and the false positive rates to be equal across different demographic groups. And when we are more interested to cases where the model makes correct predictions, we will use equal opportunity, which basically just enforces the same true positive rate across groups. So given those fairness definitions, a lot of methods or algorithms have been proposed to enforce those metrics, and they are mainly grouped in three categories, where you have like pre-processing techniques that would basically try to enforce the constraint at the data level by means of learning representations or upsampling or downsampling a certain group of samples, such that the downstream task will have data fairness properties. And then other methods focus on in-processing techniques where we change the objective function by either adding a constraint to the loss functions that will basically enforce the model to also satisfy those constraints, which are basically the disparities of the model. And when it is difficult to change the model, or we cannot retrain the model, we can use post-processing techniques that basically change the decision boundary by either changing the threshold for different groups or adjusting the model output such that it will satisfy the fairness properties that we want. However, most of this work focus rely on the strong assumption that the model has full access to reliable demographic information, which may not be true in many real-world scenarios. In general, in this work, we're interested in basically settings where we have only partial demographic information available. So there are many reasons for that. One of the most common could be during data collection, the demographic information was not mandatory. And as people are more concerned about their privacy, some users may refrain to provide their demographic information. And for that, we, uh, we have after collecting the data, we will have basically two subsets. A subset of users that have provided the demographic information. And in our setup, we assume that we have two data sets. One data set where we have the target variable, and another data set where we only have demographic information. So what is the general approach here? Like, people will tend to use the data set with demographic information in order to train an attribute classifier that will predict the missing demographic information. And basically, they apply fairness constraints on the proxy or the predicted demographic information. But the problem is that this kind of method generally results to worse trade-off between fairness and accuracy, which we aim to address in this work, where we basically aim to improve the fairness accuracy trade-off of machine learning models when we have access to limited demographic information. And for that, our method is based on one core hypothesis that we try to provide evidence to support it, where we hypothesize that the uncertainty of the sensitive attribute plays an important role in controlling the fairness and the accuracy trade-off of the model. And this hypothesis is backed by the intuition that first, the model can hardly discriminate against samples with uncertain demographic information. And also, if we enforce fairness constraints on sample with uncertain demographic information, this may have a negative impact on the trade-off that we achieve when we compare to what we would have achieved if we train the model using the true labels. So for that, we propose a framework to handle fairness under demographic scarce regime, which we call fair DSR. And our method basically introduces uncertainty awareness in the attribute classifier. And we have a two-stage framework where in the first step, we train the attribute classifier with uncertainty awareness, where we also predict, quantify, and minimize the uncertainty of the sample during the training. And in the second step, we basically print out samples with unreliable or uncertain sensitive attributes, and we apply our fairness constraint on the remaining data. And following our hypothesis, we show that this can actually improve the fairness accuracy trade-off of the final model. So I will now go through in detail for each step of our framework. As I said, in the first step, we train the attribute classifier with uncertainty awareness. And for that, we use basically Monte Carlo dropout to measure the uncertainty. However, since the training is very noisy, when we stop at a very specific epoch, we may have like different uncertainty measure at different epoch. So for that, we leverage the technique that we call like the main model, where we aggregate the measure during the training by basically averaging the model weights during different stage of the training. So for that, we use a student teacher framework. So here, the terminology may be, it's important to note that this is not just like some kind of transfer learning, because here the student and the teachers have the same architecture. So you can see the teacher as a copy of the student, but that just tracks the moving average of the student during the training. So we also call the teacher model here the mean model. So that's why we basically regularize the student model to ensure that the predictions remain consistent on sample with low uncertainty, and the uncertainty is measured by the teacher model. So they have the teacher and the student have the same architecture, just that the teacher is the moving average of the student weights during the training. And next, how we estimate the uncertainty. We apply t-stochastic forward passes on the teacher model, and then we obtain a set of predictions. And then we just measure the entropy of that set of predictions. That will tell us how reliable is our predictions. And we saw that using the teacher model, since it's the mean of the student model, this gives us more robust and reliable uncertainty measure than just using the student model at a very specific training epoch. That we showed in the paper how this impacts our results. So basically, we train the student model or the attribute classifier with a double loss. We have the classification loss, which could be the classic cross-entropy loss, so binary cross-entropy loss, since we have binary attributes. And then we realize it using the consistency loss, where we basically enforce the student to be consistent, the output to be consistent on sample with reliable sensitive attributes. And those samples are basically samples which the uncertainty measure is lower than a certain threshold. And the threshold here is updated during the training using a Gaussian moving like Gaussian growing value. So we start with a very high value, and then we keep decreasing to ensure that the our training does not just degenerate. So that's why we keep updating the threshold during the training from higher value to smaller value, depending on the epoch, such that our model will focus more and more on samples with reliable or low uncertain sensitive attributes. So we showed the benefits of the consistency laws, that how it helps us to obtain a more reliable uncertainty measure instead of just using a single model or the single output of the model. In the second stage of our framework, as I said, we enforce the fairness constraint on a subset having reliable or low uncertainty the attribute predictions. So after the first step, what we obtain the pseudo attribute which are predicted value, and then we have the uncertainty of those predictions. So we basically just prune out those samples with low uncertainty, with high uncertainty, and then we train our fairness model on the remaining data, which are the data with low uncertainty in their predictions. And as fairness mechanism, we apply exponentiated gradients and adversarial debasing, which are state-of-the-art methods, provide more details in the paper. However, since our hypothesis is built about training the model on samples with low uncertainty, we also tested the other variant of the hypothesis. So what happens if we train the model on sample with higher uncertainty? So for that, this can also address some ethical concerns that occur when we predict the sensitive information of people. So instead of using the predicted sensitive attributes, a variant of our method will be to just use the estimated uncertainty of the predictions. And for that, we can prune out samples with higher certainty or lower uncertainty in the predictions. And then we train the fairness model without any fairness constraints using sample with higher uncertainty of the sensitive attribute. And we actually show that this should follow our hypothesis that the model can hardly discriminate against samples with high uncertainty. And the last variant of our method, we basically combine them, since if the both other variant will prune out certain data points, which can impact the accuracy. So here, instead of pruning any data, we maintain all data points, and we just weight our samples based on the uncertainty of the sensitive attribute, such that sample with higher uncertainty will tend to receive lower weights during the training. So for the evaluation, we use several datasets, different variants of the adult dataset, the COMPASS, LSAC, and SEREP datasets. We provide more data about the dataset in the paper, and we consider different base models: random forest, Logistic regression, and gradient boosted trees. And in the first set of experiments, we compare our method with the ground truth sensitive attribute. So what happens if we train the model using the true attribute and compare with the model trained using the pseudo or predicted attributes? And we also compare the model, what if we do some data imputation using the k nearest neighbors to assign the missing sensitive attributes. And for that, since we're going to evaluate, we wanted to evaluate the trade-off, we used different fairness violation threshold, which basically says how strong we want to apply our constraints. And for example, when lambda is equal to 0, it means that we want strict fairness, so we want 0 disparity, and this also negatively impact the accuracy. So for each value of lambda, we perform 7 runs and average the outputs, and then we plot the Pareto fronts of the Pareto front between fairness and accuracy of final predictions. And in the second set of experiment, we compare with other methods that use that enforce or improve fairness without any demographic information, and then we give more data about this other baseline in the paper. So the first result that we obtained here is that we first measure the uncertainty of the sensitive attributes and see how this relates to the fairness of the final model. So here the models are trained without any fairness constraints. And you observe that the both variant of the adult and the new adult datasets in the old adult datasets, you see that the uncertainty is low, and then it tends to have higher disparities with different fairness metric, demographic parity, equalized hope, and equal opportunity. But in the new adult data sets, we tend to have higher uncertainty and we have like lower disparity or better fairness properties. So this also aligns with our intuition that the uncertainty has a role to play with it, and we see similar trend on the other data set that we considered. So here we have the Pareto fronts of our method compared to other model trend with different way of obtaining incentive attributes. So we can see that on the compass in the other data set, our method tends to provide the beta Pareto front. So here the beta is the left topmost data points are the beta. So we see that proxy or the model using KNS label tends to provide the worst trade-off, while the model using the deep neural network, like the prediction from the model using all the data points, it's close to the ground truth. And then you have CGI, which is another method of obtaining the pseudo attribute that we present in the paper. So this apply also when we use logistic regression as the baseline, while we use standard forest in the previous experiments. And we saw the same trends when we use like gradient boosted tree, and then we can see that our method can consistently provide beta trade-off compared to the other baseline that we considered. And we see the same thing on the other data set. So here we just presented two data sets, but the other results are in the paper. And then we also compare with adversarial debiasing, where it also shows similar trends. So our method should be also tested on other fairness enhancing mechanism. So we also do an ablation on the variant of a method where we train the model without any fairness constraint, but use it sampled with uncertain sensitive attribute. What we can notice is that the more we use uncertain samples, the better fairness gets, while we have a drop in accuracy. So this shows that across data sets, if you just train a model without any fairness constraint, but using data with higher and higher uncertainty, this tends to provide like better fairness property. On the L-star data set where the uncertainty is already very high, we see that there's no change because most of the samples have uncertain sensitive attributes. And we also analyze the effect of the uncertainty threshold. And on the adult data set, we see that the more we tight the threshold, so here 0.1 means that we use more reliable only samples with very, very low uncertainty in the sensitive attribute. And we see that when we increase the uncertainty threshold, we tend to have like worse trade-off in terms of Pareto front between fairness and accuracy. So we also tested our method using different methods of uncertainty measure. Here, for instance, the conformal prediction. So we basically showed that even a different but reliable uncertainty measure also verify our hypothesis. So here, conformal prediction basically give us, instead of predicting one label, we predict a set of labels with a strong theoretical guarantee that the true labels is inside the prediction set. So the prediction set, when it's equal to 1, it means that the model is very certain about it. But when the prediction set increases, it means the model becomes more uncertain about the prediction. And here we do not need any threshold in order to do that, because the conformal predictions, how we obtain the prediction set, already can do that by automatically computing the pressure, including a label in the conformal set or no. So for that, here we obtain basically for different coverage. So here epsilon 0.05, it means that we have like 95% probability that the conformal set contains the true labels. And the more we increase, we reduce the coverage, the more we have more uncertainty. So we see that our hypothesis also apply, where with very small coverage, we have like better trade-off, but as we increase the coverage, the trade-off gets worse. So this also verifies our hypothesis about the role of the uncertainty of the sensitive attribute. And following that, we also see what happens with different conformal or with different prediction sets. So if we train the model without fairness constraint using samples with a conformal set or the prediction sets have like two labels, it means that it's very uncertain. And we compare also with sample with model trained on sample with low uncertainty, basically samples where the prediction set is equal to 1. So we see that by training both models, so here we use all the data samples, we have this level of fairness across different metrics. But if we only use samples with certain or with low uncertainty of the sensitive attribute to train the model without fairness constraints, we see that the accuracy can get better while the fairness get worse. But if we only use the samples with high uncertainty of the sensitive attribute, it means samples with prediction sets equal to 2, then we see that unfairness or fairness get better at the cost of accuracy. And we also compare with the other baseline that the existing method to enforce fairness under limited demographic regime, and the result in the paper show that our method can consistently achieve better trade-off than those baselines. So other tables are in the paper for more details. So with that, I will conclude. So in this work, we propose a method to handle fairness in limited demographic regime. And for that, our method introduces uncertainty awareness in sensitive attributes. And we demonstrated that the fairness accuracy trade-off can be controlled or can be improved if we enforce our constraint only on samples with low uncertainty. And our method can also be useful to select data points that provide certain data fairness properties for downstream tasks by basically collecting data points with low uncertainty in the sensitive attributes if we do not plan to apply any fairness constraint on the downstream task. And for future work, it's very important to back our empirical findings with some theoretical results that will basically characterize fairness violations bounds based on the level of uncertainty of the sensitive attribute. So with that, I will thank you. There's a QR code to our GitHub repository for the code of the paper. So thank you for your attention, and do not hesitate to contact us if you have any further question. Thank you.